Do you know what energy really is? Like, can you actually picture it, imagine it in your mind? Well,
Huh?
it's not that hard and it's not abstract. It's something very concrete. I'm going to go over it very briefly with you so that you really understand it because it is extremely important to know, have a strong understanding of what it is in thermodynamics. So what it is, it's the total energy within the system. And that's the key, is within. See, the soccer ball, if it's moving, it has kinetic energy, but not because of internal energy. Internal energy is the energy within it, so of the atoms and bonds and everything like that within the soccer ball. So internal energy, it's comprised of kinetic energy, and kinetic energy is translational, vibrational, or rotational. And in thermodynamics, we're mostly concerned with the translational, so the movement like X, Y, and Z movements. Also, it's comprised of potential energy, so that's the energy between the atoms and molecules, kind of within the bonds, intermolecular forces, things like that. So if you see in this schematic right here, this is an example of repulsive forces. So they get close to each other and they repel each other. There's also intermolecular attractive forces. There's also mass energy, electronic orbital energy, subatomic energy, all of those things we usually don't care about too much in thermodynamics. It's mostly the translational and kinetic energy and this potential energy between the atoms and molecules. Okay, so internal energy is the total energy within the system, and U is the symbol for internal energy. It's a state function, so it describes the state of a system as it is. So for example, this is, say, some system in state 1. It has some internal energy value. If we heat it up, say the molecules are now moving into a gas, that's now another state. Here, internal energy is low in state 1 because there's not as much kinetic energy, and higher in state 2 because there's a lot more kinetic energy. They're moving, there's more energy that's been put into it. So it's a property of the system. That's super key. The change in internal energy, and I know this seems super basic, but this is very important when we start talking about path functions and state functions and things like that. The change in internal energy equals the internal energy final, the final state, minus the internal energy at the initial state. But we don't care about what the internal energy is at any given state, and it's actually very hard to calculate that. What we care about in thermodynamics is energy transfer. So we care about changes in energy and we care about changes in internal energy. We don't care about U itself. Okay, so the first law of thermodynamics for a closed system, very simply, is just another take on the law of conservation of energy. Energy can go into the system or it can go out of the system. So if we have our system here, this can be whatever system we want. It could be a gas, a solid, a liquid, a machine, doesn't matter what it is, any system. We can transfer energy in as heat, Q. Energy can come out as heat. Energy goes in when work is done on the system, and energy goes out when the system does work. The change in internal energy, it equals how much energy comes and goes as heat plus how much energy comes and goes as work. And that's literally what it is here. Delta U equals Q plus W. So if energy goes into the system, the internal energy goes up. Big surprise. If energy goes out of the system, then the change in internal energy goes down. It's now negative. This is the International Union of Pure and Applied Chemistry convention, having the plus sign right here, where energy goes in. So that's going to be positive. Energy goes out, that'll be negative. So in this convention, work is greater than 0 when energy goes in. If you do work on the system, that's positive work. And out is like the reverse. You might see in other courses or other conventions in like your physics engineering course or whatnot, sometimes they'll use the negative convention. That's totally fine as long as you're consistent. So if there's a negative here, then energy in means work is negative. Energy is heat, that's Q, into the system. And if you do that, it's going to change state from some initial internal energy to some final internal energy. And the change in internal energy, kind of as you incrementally go from the initial to final state, in an infinitesimal change is going to be du, right? This infinitesimal change. And that allows us to write the first law in infinitesimal form. du equals dq plus dw. It's the first law, differential form. Now this dq just means a little bit amount of energy is heat, not like the change in energy is heat, and same for the work. So we have these two conventions right here. If we integrate this, integrate our life away, we now have, this is kind of the integral from the initial to final state. Q and W are path functions. It's just like summing up all the amounts of energy being transferred as heat or work, which gives us the total energy transferred as heat or work. But for internal energy, because it's a state function, we can integrate this just like normal Calc 2 stuff. The integral of du is u from the initial to final state, and this equals the change in the internal energy plus the heat and the work, which gives us delta U plus Q plus W. All right, that's the first law in thermodynamics in all its glory. Hope you enjoyed it. See you in the next video. Cheers.